All right, we're going to start chapter 12, non-renewable resources. I have the note packet on Classroom, so you guys can download that and go ahead and print it if you want. If you're having issues accessing it, just let me know. I know on mobile devices, if you try to open up some of my Google Drive documents, they won't open up because I do them from my personal Gmail account, and with KUSD, they don't allow you to share from a personal Gmail account to a KUSD account. So try it on a computer. If you still can't get it, I can always send you a PDF or something else. So the first thing we're going to talk about, non-renewable and renewable energy resources. We talked about these a little bit at the beginning of the year. So non-renewable, finite supply, limited supply. So what are some examples of those? Fossil fuels and nuclear energy. So any type of fossil fuel that we talk about, whether it be coal or gasoline or natural gas, we'll talk about all of those. Renewable can be reused. So biomass, those would be bio meaning living, right? So those would be like plants, like burning wood. Hydro, that'd be like your dams and your water. Geothermal, geo meaning rock, thermal meaning heat. So geothermal. Wind, like wind turbines, and solar, as in like solar energy. So we'll talk about all of these. This chapter is just on non-renewable resources. Next chapter is on renewable ones. But what I find is that a lot of students already have a pretty good idea about the renewable energy sources. You don't need to know a ton about them. So we're not going to go super in depth. All right, so fossil fuels, we've talked a lot about these. They come from fossilized remains of organs. They include 3 different types that we're going to talk about that you want to write down: oil, coal, and natural gas. Millions of years to form. This is why they're non-renewable, is because they take a really long time. What typically happens, if you take a look over here, we get dead tree and animal. I know some poor person did this cartoon with a frowny face and a tree. And then they get covered up by dirt, by plants, and then over millions of years, heat and pressure in just the right conditions, they end up forming. Typically, they're forming in anaerobic environments, which means without oxygen. And a lot of times this is happening on like swampy areas and ocean floor. So if you bury your dead dog Fido, he's not probably going to turn into a fossil fuel. He needs just the right conditions in order to become coal. Not to mention, you'd be there waiting for 50 to 350 million years, which would not be very awesome. All right. So most use energy sources. So let's take a look at this chart. This goes from 1990, and these are projections to 2040. On the side, quadrillion, BTU. BTU stands for British Thermal Units. It's just an energy measure. So if we take a look, obviously this was done in 2012. So you can see this line right here. We're up over here. So we're going to assume that we're right there with the projections. So the top 3 energy sources that are used currently are these 3, right? Natural gas, coal, liquid fuels. So you want to write those down. You'll notice all of them are pretty much increasing except for which one? Which one is not increasing? So coal is definitely not increasing or increasing as much. And the reason for that is because we're actually running out of coal. So we'll talk about that one. The fastest growing, let's take a look at the slopes. Which do you think are the fastest that are increasing the most or projected to increase the most? Renewables and natural gas. You don't necessarily need to memorize that per se. They don't necessarily ask a ton about those types of things. They will ask you what are examples of renewable or non-renewable in the multiple choice. And then they will ask you about specific different types of these non-renewables and what are some of the pros and cons. But I'm just giving you some background information here. So in the US, if we take a look at this, okay, we can see oil right here. We got natural gas and we've got coal, okay? Nuclear energy increasing quite a bit, okay? Coal actually was increasing a bit. So this is the US versus this is the world, okay? So we're just looking at the US now. Coal is going to start to level off here, but this is just comparing what the US uses to what the world uses. And you'll notice we have some sharper inclines here. We do have quite a bit of oil and quite a bit of coal in the United States, so we're able to mine them here and then get those resources. So let's look at per capita. Per capita, you need to know that. What is per capita? Per person. So energy consumption per person. Oh, hey, look, the world is down here at blue. Okay, we've got China, we've got Europe, FSU, don't ask me what that is. I have no idea. And then we have the US. So the US energy use is 325 gigajoules per person, which is 5 times greater than the world average. So we in the United States use a lot more energy. No surprise to anyone else, we use a lot more of everything else as well. Produce more CO2, we consume more meat, we use more water. So which countries use the most energy? You can just write United States. I know it says which countries. It's probably more like which continent here. So let's take a look at this chart. It's a little bit tricky to read, but once I explain it, you'll totally get it. So over here on the left-hand side, we get a measure of how developed a country is. So if we're up here at the top at like 95, it's a really developed country, okay? It's just a measure of how developed the country is. Down here at the bottom, how much energy they use. So this is a lot of energy, okay? So if we take a look at the countries that are using the most energy, notice they're high up over here. They're pretty developed. What about the countries using a really low amount? Oh, notice they're not very developed. So we can actually draw a line and have a correlation here showing us that the countries that are the most developed are the ones that are actually using the most energy. So on that line where you wrote the United States, you could also include that the developed countries use more energy. And we know that from previous units. So when we talk about energy, it looks very different in the United States compared to other countries, or in developed countries versus developing countries. So in developed countries like the United States, okay, commercial energy sources. So commercial means selling, right? So those that are bought and sold. So we sell and buy a lot of coal and oil and natural gas. You buy it from the electrical company. You pay your electric bill. You buy gasoline from gas stations, all of that stuff. You're buying it, you're selling it. In places that are developing, think Southeast Asia, a lot of parts of Africa, they use subsistence energy sources. You don't really need to know the word like subsistence, but I want you to understand that people in these developed countries, they're not putting together and gathering all of these energy sources to sell them to other people and to have these big companies that are creating oil and natural gas and coal. What they're doing is they're literally just collecting energy, whether that be firewood or animal dung or straw, so they can cook and they can eat. So it's very different between developed and developing countries. Only 20% of the world's population lives in developed countries. But that 20%, we are in that 20%. Remember, developed countries, United States, Canada, Europe, Australia, uses 70% of the world's energy. So again, the developed countries are using a lot more than their actual share. And you can see energy consumption by person. The darker colors represent higher energy consumption. So Canada and US, Australia, Saudi Arabia, and that's because Saudi Arabia has a ton of oil over there. And then parts of Europe, Russia, Greenland. All right, so we're going to talk now about energy return on energy investment. So all fuel takes energy to obtain. If you're getting straw and sticks, you're going to go pick it up. If you're drilling for oil, you need energy for the equipment to go drill in that oil or to dig up that coal and make a coal mine. So energy return on energy investment right here is the amount of energy we get out of an energy source for every unit of energy we expend on its production. I want you to write this down because it's kind of important. It's important to understand, but they don't test you on it really on the AP exam. So I want you just to write, don't memorize. The reason I want you to know it is because it's a big deal when we talk about coal, okay? So how much energy do we have to put in to get our coal or to get our oil or to get our gas? Here's the problem. As we run out of some of these resources, we have to take more and more energy to dig down deeper and find them in places where they're not really easy to get to. So if we take a look at our different fuel types, okay, this shows us energy return on investment, meaning how much energy does it take for us to get these types of energy, okay? High number is good. So if we take a look, nuclear energy, we haven't talked about that yet. We'll talk about that at the end of this unit, but nuclear energy, 75, that's really good. Doesn't take a lot of energy for us to get the uranium that we need for nuclear energy, and then we're able to produce some energy from it. Hydro, 49 and 35, it's just talking about energy storage. Coal is 30, this is why we use a lot of coal. Gas, then we get solar, wind, biomass, and a different type of solar. So you can see why we end up using coal. You might ask, well, why don't we use more hydroelectric, like dams? Why don't we use more dams? Well, there's only so many places we can put dams, so that's the problem. Why don't we use more nuclear? Well, we're going to talk about that. And they're actually predicting that nuclear energy is going to be increasing in the future. So coal, this is important. They like to ask a lot about coal. We'll do a section on coal, but coal is it's energy return on energy investment. So meaning, in the early 1900s, we had a lot of coal everywhere. You didn't have to dig very deep to find it. You didn't need to use a lot of machinery. You didn't have to go fly to Alaska to dig up coal. You could just find a lot of it right below the surface. So we got a lot of energy. We didn't have to use a lot of energy to get it. You'll notice we're right here, okay? The amount of energy that we're putting in to get this coal now is a lot more. Why? Because we've started running out of it. And it's no longer easy for us to dig and get it wherever we want. So we have to go to these remote locations or dig down super deep in order to get the coal. All right, so we'll do second law of thermodynamics, energy efficiency. We'll basically finish this page of notes and then we'll be done. So this is a reminder of the second law of thermodynamics. They always like to ask about this on the AP exam, so put a star by it. Second law of thermodynamics, when energy is transformed, its ability to do work decreases or diminishes. We've talked about this, okay? If I have an energy source, right, and I have to go use mechanical energy to extract it, and then I have to use more electricity to process it, and then I'm gonna burn it, okay? And then I'm going to use it to produce electricity. Every time we go through one of these arrows and we use energy and we change it from one energy form to another, we're losing energy. And remember, we lose energy as heat. Our classic example, if I've got electricity going into, let's say, a light bulb, my terrible light bulb, okay? So I've got electricity coming in. What's going to come out of that light bulb? We're going to get light. Oh my goodness. But we're also going to get heat. So some of it's going to be lost as heat, and that's why the light bulb is hot. So not 100% of the energy that we put into something can actually be used. So energy efficiency, put a star. They like to do math problems on these. We'll do some math problems. What is energy efficiency? A measure of how much energy is conserved during a process. Okay, so how much energy are we using or are we losing during a process? If it was perfectly efficient, right? We have my little light bulb, okay? And then we're converting it from electricity into light. If it were perfectly efficient, I would put in 10 joules here and I would get out 10 joules of light. But that's not the case because some of it's lost as heat, okay? So perfectly efficient, I would put in a certain amount of energy and I would get that same energy out. So they like to have you calculate energy efficiency. So here's the equation that I would like you to write down. Energy efficiency, you take the energy that comes out, you can just write energy out divided by the energy you put in, and you times it by 100. So you should get a percentage. So in my light bulb example, if I put 10 joules of energy in and 10 out, that's going to give me 10 divided by 10 is 1 times 100, which is 100%. Nothing is ever 100% efficient, but we want to get it as close to 100 as humanly possible. So let's look at these two problems. An incandescent light bulb uses 40 joules of electricity to produce 1 joule of light. What is the efficiency of the light bulb? If we go back to our equation says we need energy out over energy in. So how much energy came out of the light bulb? 1 joule. How much energy came into the light? 40 joules. Okay, so you take 1 divided by 40 and then times 100. You're going to get something like, I don't know, something a little less than, let's see, 1 out of 40, I don't know, something around 1%. Okay. Sorry, I didn't use good numbers that I can do in my head. All right, a CFL light bulb uses 10 joules of electricity to produce 1 joule of light. What is the efficiency? So how much came out over how much did we put in? 1/10 is 0.1 times 100, 10%. Okay, so which light bulb is more efficient? Again, you've got something over here that's like, I don't know, 1 to 2% and 10%. So which is more efficient? This guy, compact fluorescent. These are the curly Q light bulbs that you see. They don't really look, they look kind of like that, but not really. And this is a regular light bulb, like the old-fashioned ones. So that's all you have to do to figure out energy efficiency problems, okay? So if we're looking at, I want to give you an example, hot water heaters. Again, with the second law of thermodynamics, let's take a gas water heater. It takes natural gas and turns it into heat. It's 80% efficient. An electric water heater takes gas or fossil fuels, turns it into electricity, and then turns it into heat. It's only 35% efficient. Why is this one less efficient? Because it's got 2 energy transformations here. So whenever we have more energy transformations, we're going to have more energy lost. So the fewest amount of conversions is going to be the most efficient. Let's take a look at transportation. So most efficient transportation methods. So we can take a look. Less efficient is over here, how much energy they're using. More efficient over here. Cycling and walking are the most efficient. And we also have a light rail, bus, some trains. Okay, then we got a motorcycle, cars. So walking, and then public transportation, right? So where you're sharing a space with other people. So walking, cycling, public transportation. And this is why, because we can use less energy to carry more people, or we're using the same amount of energy, but we're carrying more people. So per person, it's less. Last thing we're going to do, energy conservation. So reducing or going out without a service to save energy. So to conserve is to save, right? So how am I going to save energy? Well, turn off the lights, walking instead of driving. Some people get this confused with energy efficiency. They're very similar. Energy efficiency, you're talking more about the process of converting energy, whereas energy conservation, you're just not using something so that you can save energy. Okay. All right, awesome. So that's where we're going to end. If you have any questions, please send me an email, and that's it.